Okay, so let me know if it is not visible. Okay. Yeah. So previously, like in the previous talk, uh, we covered that when you have a transition state, like we basically derived the transition state theory, where we have these typical V naught. This is your state A. This is your state B, and we know that there is an equilibrium between these two states. But once it crosses the transition state barrier, there is nothing. Like there's no equilibrium. And we derived that K after several after debunking, or not debunking exactly, but after addressing several assumptions, initial assumptions, we said that K is equal to what is that? Like, but like for a one-dimensional TST, we said that basically, no, no. Yeah. So accounting. So we basically, the final equation was, it is mu naught divided by 1 plus mu naught tau naught into e raised to minus v naught by kBt. So this was the final equation that we had looked at. So we had initially made 4 different assumptions. One is that there is no recrossing. Second one was that it is a classical system. Third one was third one was that the energy redistribution is faster. Diffusion is faster. And the fourth one is ballistic motion.
Wait, can you remind me what energy redistribution faster means?
That tau naught is like much
Okay.
lesser than your K inverse. So the amount of time that your system needs to go back to the original Boltzmann distribution is way lesser than the time required for the states to go across. So basically this means that there is a continuous supply of there's a continuous supply of system, like the system equilibrium is not being affected. So these are all uh, the kinetics is not affecting the equilibrium directly. So this particular equation that we had, we were able to address this particular assumption, the energy redistribution when it goes away. Like that is why we have this tau naught factor here.
Yeah.
To account for if the rate constant is not actually much bigger than, like, to account if the rate constants are like pretty big, like the amount of time required for the system to go from this state to this state is actually much faster as compared to the amount of time system needs to actually go back to its original Boltzmann distribution. So this accounts for the energy redistribution, but these two will be there because transition state theory does not deal with recrossing. Which is why we actually cannot comment on the backward rates. Like there have been certain approaches which may have been able to do that, such as the Bennett-Chandler approach, but they're still not. They're still based on certain more assumptions. So the thing is that using transition state theory, it is really difficult for you to get the backward rates of a reaction. The only thing that you can do is get the forward rate. So if you're going from A to B, transition state will only give you K A to B. But if you want to get the backward rate, then you actually have to apply the same transition state theory to find the rate B to A, and that will be your backward rate. That's the only way you can do it. So there was one more assumption that we made where we said that the motion of the system is ballistic, or the particles are ballistic. So once it starts going towards here, there's no interruption at all. It just directly goes. Right? There is no going back, going forward, going back, going forward, going back, going forward.
Yeah.
Right? So the next part, the diffusion transition state theory basically takes care of the situations where ballistic motion is not where ballistic motion is basically not applicable. Right there, so so ballistic motion is not applicable in systems where your rate constant is like too slow. When your rate constants are too slow, then it means that there is some inherent which means that the transition from A to the transition state itself is not slow. It is not fast. It is slow.
So in general that occurs like when there's like a very high energy barrier, right?
Yeah, when there's a very high energy barrier, this generally occurs. Yeah. So ballistic motion is the fastest motion of the particle from the reactant to the transition state. So because there is no interruption occurring at all. So so this happens when the reactions are typically fast. Again, as
Right.
I said, when you have a acid-base reactions and all, yeah, then you can assume that ballistic motion takes place because the motion is very fast.
Okay.
But when you're looking at slow reactions, then ballistic motion is not really applicable because ballistic motion actually tends to overestimate your rate constant. This is when you look at the ballistic motion where where basically your frequency factor mu naught is where your nu naught is basically where your nu naught is basically kVt by 2 pi h bar divided by 1 plus kBt by h omega naught, h bar omega
Okay.
naught. So this is your frequency factor, and this comes from ballistic motion, right? So what this essentially says is that when your omega naught frequency factor is too low, then this particular factor is too high. So what you end up with is omega naught by when your omega naught is like pretty low, much lesser than infinity, you basically get your frequency factor to be omega naught by 2 pi. But whereas when your omega naught, when your frequency tends to infinity, it cannot go to infinity. Your frequency factor cannot become infinity because there is an inherent limiting factor which depends on temperature. So there your frequency factor instead becomes, so your omega naught becomes too high. This whole factor is 0 compared to 1. So you are left with kBt by 2 pi h bar. So as I said, these two frequency factors are not taking into account the width of this particular minima. Because we are saying that the motion is ballistic. So when you say the motion is ballistic, it is so fast that your width doesn't matter. That is why your frequency factor essentially becomes dependent on the frequency of oscillations. So this is an upper limit. Like this is an overestimation. This might be an overestimation if ballistic motion doesn't work. That is why uh, that is why this particular thing we call it as ballistic limit. I don't know if you have heard this before.
No.
So basically we can write any rate constant as some frequency factor into e raised to minus v naught by kBt, right? So there are two limits. One is the upper limit, which is called as the ballistic limit. Ballistic limit. So the ballistic limit is basically the maximum possible frequency factor or the maximum possible constant. So when you come to this case where A is equal to kVt by 2 pi h bar, this is the maximum possible frequency factor that can happen in any case. Right? Like you can't go beyond this because if you go beyond, you'll be violating all thermodynamics of the system. So this is the ballistic limit, and next what we'll look at is in second part is basically the diffusion limit. Like what is the other thing? So when you say that your K is typically less than K ballistic and will always be less than K diffusion. So the lowest possible, which is determined by your diffusion transition state theory. So is it fine till here?
Yes.
I mean,
Okay.
yeah. So the reason why I'm still keeping classical system is that when you go to quantum systems, quantum tunneling will be present. So quantum tunneling is something which is a full lecture on its own.
Yeah.
So I'll just erase certain parts. Yeah, I mean these equations I can't remember on the top of my head. That's why I'm referring to my notes. Wait. For now, let me just erase this because. So did you do mass transfer when you were in undergrad?
Yeah, undergrad, yeah.
Yeah, so maybe I'll just start from the intuition, like how diffusion coefficient is looked at from an engineering perspective, like how we do it,
Mhm.
and then I'll give a statistical mechanics perspective as to how the diffusion coefficient is actually a true quantity which can be derived. So so if you look at like now we'll start with diffusion. We'll just talk about diffusion first and not diffusion DST. We'll go to diffusion DST later on. So you have heard of Fick's law, right? Fick's first law,
Yes.
right?
Yeah. Concentration difference, the system moves from
Exactly. So the flux that you have, J, is equal
is
to minus
minus
E del C by basically your
rho C by dou X.
gradient of your concentration, right?
Yes.
So when you write it in 1D, your flux J is equal to minus D times in just in a 1D, dC by dx, right? So
Yes.
the reason why this is called Fick's first law is because diffusion coefficient here is only seen as a proportionality constant. So this is not exactly Fick's law, it's not exactly derived. That is why it is a law, right? So what it is said is that your flux when you're going from a state when you're going from A to B, the flux is proportional to your concentration difference. But if I say if you have some say fluid or something, some particles moving from say state 1 to state 2, right? This is the flux that you want to measure. What will be the flux be proportional to? The flux will be proportional to the concentration difference between 1 and 2, C1 and C2.
Yeah.
Right? High. So this is our driving force. This is the driving force. So larger the concentration difference, more is the tendency to go from 1 to 2. Driving force, and your J will be inversely proportional to the length. Right? You might have a larger concentration difference, but if your length, the traveling length is like much farther, then you will have then naturally your flux will be lower because your length is negatively affecting it, inversely affecting it. So then what came is that okay, now let's just combine these two things. Your flux will be proportional to C1 minus C2 by L. Okay, and now if we replace this L by delta X, it will be proportional to delta C by delta X. And if we make everything infinitesimally small, like if this L is like dx and this delta C is like dc, your J will be proportional to dc by dx. Now, how do we remove the proportionality? We remove the proportionality using the proportionality constant, which is J is equal to some constant d into dc by dx. And it should be minus d because we are going against the length.
You're going towards the lower.
Sorry, we are going towards the lower concentration. So it will be minus D. So that this is your proportionality constant.
Mm.
And what fixed first law says is that diffusion coefficient might not have a significant it might not have a physical significance because but your diffusion coefficient is just a proportionality constant between your flux and your concentration gradient.
Yeah.
So if you look at all the in chemical engineering, we do certain experiments, to look at the diffusion coefficient of acetone and all that. The observables, what we observe, are actually the flux that goes, which is basically like moles per second divided by area, the area in which it is. So we look at the flux, we look at the concentration gradient, and we basically do a linear
Plot and get a slope.
and get the proportionality constant, which we call as a diffusion coefficient. So this is how Fick's first law came into effect.
Okay.
Diffusion coefficient is a proportionality constant according to Fick's first law. But if you actually look at and from here, you go into if you apply Stokes-Einstein equation and all that, you get means for displacement equal to 6dt. You apply Stokes-Einstein, you get that it comes. So there is a way in which you can get the expression for mean square displacement as mean square displacement equal to 6dt in a 3D space from continuum mechanics, from fluid mechanics. So now instead of looking at just Fick's law as Fick's law, like just as a proportionality and a proportionality constant, there is a way in statistical mechanics in which we can actually describe what diffusion coefficient actually is. We can give some physical significance to it.
Random walk.
So that is a power of I think that is the power of statistical mechanics personally, because it is actually able to give meaning to seemingly unphysical things. For example, like one of the biggest things is basically entropy. Entropy was initially when the second law was formed. Entropy was actually used in order to satisfy the second law. It was thought of as something which might not be calculated or might not have a physical significance, but statistical mechanics did give. So similarly, I think this is one other example as to why stat mech is important. So suppose you have a particle. Suppose you have a particle here, and you want to see it diffuse. So this is your plus x direction. This is your minus x direction, right? And say that the minimum distance that it can actually hop is k0. The minimum distance that it can. So basically, like it can hop like this, like this, like this, like this, or it can hop basically like this, go back. So it can basically go like anywhere, right? So basically, we're looking at a random walk, but like random. This is I would write it as basically random hopping. It's trying to hop. Random hopping. So say we have say the particle has made n jumps, right? So what will be your what will be the position after n jumps?
N times x jumps for sum of sigma.
So this will be plus a naught. This will be minus a naught. So it will be some a1 plus a2 till plus an, where your aai can be plus or minus a naught, anything.
Right.
It can, so your a1 can be either plus a naught minus a naught. Any a can be plus or minus a naught, right? So what will be the mean of this?
Mostly 0.
It will be 0 statistically. Right? Because when you have a random number of jumps where your probability of going here or here is 50%, then mean tells you that you will actually be
At 0.
at 0 only. So
Mm.
your mean is 0 because you have an equal probability of going either left or right.
Hmm.
But instead of mean, what if you look at the standard deviation of your position?
Mm.
Sorry. This, what will this be? This will be
A1 square plus A2
a2 square plus an square.
n square.
Now we know that ai is plus or minus a naught. So ai square will always be a naught square.
Positive.
We get this?
Mm.
Right? N times a naught square because there are n. It has made n number of jumps. Right?
Bar is missing, right? Average is missing. A1 square plus A2 square, an square by n. If you were to average A1 square, A2 square, an square,
I think 1 second.
be n square by n. No. The square outside the bar? Oh, no, it can't be. Then it becomes 0.
1 second. Yeah, it should be outside the bar, right? Oh yeah, it should be outside the bar. Sorry. Yeah. You're right. I'm really sorry. Yeah, this should be outside the bar. Yeah.
I'm not sure. Wait.
No. You're right. I think. Uh, no, you're right. It should be like a1 plus a2 plus a3 an square. So what happens is now, yeah, I got it. So you'll get sigma ai square, and then you'll get plus sigma ai aj, where I not equal to j.
What is that? I can't. Oh, sigma AI square plus what is that? Sigma?
ai aj.
Oh, AI AJ. Oh, okay.
So
Yeah.
now this will be 0.
Yeah.
The mean of this will be 0.
Mm.
Whereas this will give you n times a naught square,
Yeah.
right? So yeah, now you're right. It will be basically n square a naught square divided by n.
Mm.
So this n will get cut and it will give you n a naught square.
Yeah.
Right? Or is it sigma
Actually,
ai?
not.
Oh no, sigma ai square will be n times a naught square. Yeah. Where did this mean come from? Mean of-
Let me look online. What's the formula?
1 second. Maybe it's a weighted mean, I guess. Yeah, but I think finally you should get this. So this will be your mean square displacement, this n times a naught square.
Yeah, it's n delta x square. Variance is n delta x square d by.
Yeah, so it is NA naught square only, no? Mean square displacement.
Correct. Yeah, it's NA naught square.
Yeah, it's NA naught square only, no? Yeah.
Mhm.
Yeah. Okay, thank you. Yeah. So we have the this is NA naught square, and so suppose, oh no, I could have not done that. So suppose the amount of time taken to jump for the particle is say tau naught, right? Like suppose a time, hello.
Yeah, I can hear.
So yeah, suppose a time required, for the particle to make one jump is tau naught. So we can, so if the time required is tau naught, then we can basically write n as n a naught square, right? So we can write n as t by tau naught, where t is the total number of time that we have observed, and tau naught is the time required for one jump, because the number of jumps into tau naught will be your total time,
Mm.
right? So we can now write this as a naught square by tau naught into t.
Mm.
Now I will write this as I'll multiply and divide by 2,
Mm.
and I'll put this in bracket 2 tau naught into t.
Mm.
So the reason why I did this is that 2 tau naught
Mm.
2 tau naught is actually the amount of time required for the particle to go in one direction, right? Like for the particle to go specifically in one direction, one
It
jump is
takes
not
2 time.
enough. It has to jump one more time towards this one.
Mm.
Then your net movement is in the positive in one particular direction.
Right.
That is 2 tau naught is the average time that it needs to jump towards one particular direction.
Right.
So now I'll write this as, I'll again rewrite the MSD as xn square equal to 2 times a naught square by 2 tau naught into t. And this is actually your a naught square by 2 tau naught is 2 dt. So your diffusion coefficient, statistical mechanically, is basically nothing but it basically measures your tendency to
Move towards what?
one direction.
Mm.
Right? It's looking at, okay, how quickly it is actually able to move towards one direction. And because we did this in a 1D case, so this basically is your expression for your diffusion coefficient, like a naught square by 2 tau naught,
Mm.
right? And this is for 1D. So if you go to 2D, because now you have to cater to both x and y, your d2d will become basically a naught square by 4 tau naught.
Mm.
It has to move in one particular x direction, one particular y direction. Similarly, so your mean square displacement will essentially become 4 dt.
Mm.
Because your n a naught square is always constant, right?
Right.
Whatever amount of steps you take. So 3d
So 3D becomes a naught square
a
by.
naught square over 6 tau naught, because one direction x, one direction y, one direction z. And your xn square will essentially become 6d.
6 dt.
So this is the famous, whatever we want to call it, MSD equation, right? right? This is
Right.
the this is the 3D equation. So like so basically this particular MSD equation from continuum mechanics, you get it from Fick's law,
Hmm.
right? Whereas we'll do something different. I think we might be doing something like reverse when you're looking at statistical mechanics.
Okay.
Yeah. So secondly, and next, so this is done, right? Yeah.
Yeah.
So now we look at like diffusion flux. Diffusion flux. So we have, say, a barrier. There are a set of particles here, N1, set of particles here, N2. Distance between them is A0. Again. Okay, so what will be your flux? Flux is measuring okay how many particles will tend to go from either side, right?
Hmm.
So your flux will
2
be
minus.
N1 times 1 upon 2 tau naught because it has to go towards that,
Okay.
right? It's basically particles per
So
second.
it's
Particles per second.
J12. It'll be
Sorry?
J12, right?
Yeah, it is J12. Yeah. No, it's actually total net flux because I'll be adding minus N2
Oh, okay.
2 tau naught.
Okay.
How many will go from
Yeah.
here also?
Got
Right?
it.
So this is basically N1 minus N2 times 2 tau naught.
Hmm.
Okay, so now because these are the number of particles, let us just write N1 and N2 capital N capital N as basically a linear density form. So basically N is equal to N divided by A naught.
Hmm.
So this has the units of 1 upon length, right?
Yeah.
Number of particles. So basically linear density of the particle density. So we can write this as A naught by 2 tau naught into N1 minus N1 minus
Into.
2, right?
Hmm.
Right. And now if you want to put this N, if this linear density is a function of say A naught or X here,
Hmm.
so we can so suppose now instead of what did I yeah, so suppose our A naught is basically infinitesimally small. A naught
Hmm.
is delta X or dx, right? Now we can write this as N1 and we can write N1 as N1 of X where it is at some position or X naught, right? Suppose this position is X naught and this position is X
Right.
naught plus delta plus dx.
Mm-hmm.
Right? It is that small. We are looking at like that small a diffusion of a fluid. So your N2 is essentially sorry, this is not N1x, Nx naught will be N of X naught plus dx, right?
Okay.
And can we so how do we express this in terms of Nx naught? We can use Taylor's expansion. It will be N of X naught plus dn by dx into dx, which basically is your A naught,
Hmm.
right? Basically, it should be like it should basically be n dash x naught into dx,
Yeah.
right? So dx is your A naught,
Hmm.
and your n dash is basically your dn by dx, the derivative,
Yeah.
right? Derivative at x naught, x naught. So let me just rub this. So now what does your J become? J is equal to A naught by 2 tau naught into N1 minus N2, which is equal to A naught by 2 tau naught into N1 is N of X naught minus N of X naught plus dN by dx at X naught into A naught.
Hmm.
Right? This is N1, this is N2.
Hmm.
So NX naught gets cancelled.
You get
What we get is is equal to A naught by 2 tau naught into minus dN by dx at X naught into A naught.
Hmm.
So now this A naught will get it here is
A naught
equal to, and minus also will get it out,
Hmm.
minus A naught square by 2 tau naught into dN by dx. And what is this? This is again diffusion coefficient. So J is equal to minus D into dN by dx. So this is essentially what? Fick's first law.
Hmm.
Fick's first law in a 1D, one dimension, in 1D. Right? Any questions? Any concerns?
No.
No, right?
Hmm.
Yeah. Okay, this is Fick's first law in 1D. And like if
Yeah.
you go for 2D and you add, and instead of number of particles, if you convert particles into concentration
Hmm.
using divided by volume and all that, you will get basically your
Dou C by dou X.
3D, you will basically get J is equal to minus D gradient of C.
Hmm.
Right, you'll basically get this. So having written this, so I'll just write this diffusion flux in 1D here, and now we'll go towards diffusion. We'll basically derive the diffusion TST. So I have written J is equal to minus D times dN by
It
dx.
does. Hmm.
This is in 1D, so because we are doing 1D TST, we'll have this. Okay.
Hmm.
So again, we come back to here, where basically this is the width of your reactant state, L naught. This is the width of your transition state, LB. Hi, are you there?
Yes.
Yeah, okay.
Oh, my camera went off for some reason.
This is the energy barrier, right? And let us say that the linear density here is 1 upon L naught, because your linear density is dependent on your length.
Hmm.
Okay, it can be anything. It can be some capital N by L naught, like it won't matter.
Yeah.
It will be some capital N by L naught, but it will go into all the constants. So
Mhm.
let us now let us say that your linear density is 1 upon L naught.
Mhm.
Right? This is your N naught. This is your initial number of particles.
Right.
Right? And now let us do one thing. Let us just magnify this particular place, the transition
Okay.
state. Okay. So I'll just again write it here, that your N naught, your actual total number of particles at the reactant state, is the density of that is 1 upon L naught.
Mhm.
Right? Where L naught is your width of like reactant state. right?
Mhm.
Now, when you get to the transition state, where this is your LB or length of the transition state, right? Let us look at it in terms of flux. So this is the starting point of your transition state. This is the ending point of your transition state, right? So what? So now suppose now this is an indicator of the number of particles. So suppose the number of particles is n hash. Okay.
Mhm.
So now it is not n naught. This is n hash, like the density at the linear density at start of TS at TS at the transition state.
Mhm.
So this is representative of the number of particles that have reached the transition state and now are going to transition. Right. So from here, the particles will start, diffusing towards the next stage,
Mhm.
towards this state. Right. And your and we know that your density will basically linear density will go down from here. Like if there will be some n of x all along the path, right? And there will be some n final, some linear density final here.
Mhm.
Like from n hash, there will be some final density or some number of particles which have reached that, which have actually crossed the transition state.
Right.
Right. So do we agree that n final is much lesser than n hash?
Much lesser.
Not much lesser, maybe, but lesser than. Sorry. It will be
Yeah.
significantly lesser than n hash. I'll tell why.
Mhm.
Okay, it will be lesser than. Okay, it will be lesser than n hash for sure.
Yeah.
But it is diffusing. It's not exactly a ballistic mode,
Mm.
right? So, but the reason why we approximate that n final will actually be 0 is because
Mm.
of recrossing. So once the particle reaches n0, once the
Mm.
particle reaches once the particle reaches nf, this particular
Right.
state, because we are saying that there is no recrossing, it will immediately go down to the product state,
Okay.
right? So there will basically be no particles left here. So whatever particles reach here will immediately go to the product state because there's no transition state and the product state.
Recrossing. Mm.
So that's why we consider our NF to be 0, which
Mhm.
means that your diffusion or your diffusion or your this thing is only from here to here. After it comes here, it immediately goes on to the product state,
Got it.
right? So now how can we write what will be the rate constant? The rate constant is basically the flux, right?
Mhm.
What is rate constant? Rate constant is the number of
The
transitions or what with what speed
probability event
are
or
they going?
unit time.
Yeah.
Mm.
So instead of flux, we will write rate constant is basically the flux in this particular
Mhm.
region.
Mhm.
So what is the flux? It is the rate constant. And what is the rate?
Minus
Rate constant is
E
minus d into what is dn. Instead of dn, it is now delta n. It
and
is
double dash.
n hash minus 0
Mm.
divided
By
by LB,
LD. Mm.
the length, right?
Yeah.
We've gotten here. So instead of your so there is nothing called as frequency factor here if you're noticing. There's no frequency
Mhm.
factor.
Mhm.
This essentially is your rate constant. Instead of a frequency factor where you looked at a number of attempts,
Yeah.
here your rate constant is essentially a flux. So that
Right.
takes care of your diffusion,
Right.
right? So your K now is minus D times N hash times
By LB.
LB.
Hmm.
Now what is N hash? So we've written like N naught is equal to 1 upon L naught. So if you look at like probabilistically, your N hash will be, if you look at probabilistically, n hash or the number of particles in that particular region, near the transition state region, will be equal to n naught times e raised to minus v naught by kBt, right? Because the probability of the particle being there is this. And
Yeah, the
original number of
Boltzmann
particles are
const.
n naught,
Yeah,
right?
got it. Yeah.
So now substituting this here, we get k is equal to minus d. Oh yeah, that's one
happened?
very big thing that I missed. Sorry. Uh, so this minus sign is actually not there. So when you're looking at here, when you have this LB, right?
Oh, it's 0 minus n
Yeah,
hash.
exactly.
Oh,
Yeah.
minus of minus. Yeah, got it.
Yeah. So this whole thing, so when you write the k is actually minus d times n hash minus 0 divided by 0 minus LB. So that will essentially mean that your k, the rate constant, is like d n hash by LB. And now since n hash is equal to n naught times e raised to minus v naught by kBt, your rate constant becomes d by n naught LB into d by d into d n naught. Let me just write it here. By L naught LB into e raised to minus v naught by kBt. Oh, sorry. No. D n naught by LB.
Yeah, L naught won't be there. Yeah, that's what
Now
I
n naught we substitute as
1 by
L
LB.
naught. That
Oh,
will give
L
us
naught.
d
Yeah.
naught by L naught LB e raised to minus v naught kBt. Right. So this is this d naught. So this particular rate constant k is equal to d by L naught LB into e raised to minus v naught by kBt. This particular thing is called as your Cramer's rate theory.
Okay.
So this is essentially Cramer's rate theory, which talks about diffusion and transition. So this is now you see that this essentially is your frequency factor, right? So when like generally when we write the rate constant is equal to some frequency factor into e raised to minus v naught by kBt, when your A is kBt by 2 pi h bar, this is what I called as a ballistic limit, right? So now similarly, if your frequency factor is diffusion coefficient d divided by L naught LB, this becomes your diffusion limit. Diffusion limit. This is also called as Cramer's limit.
Wait, so L naught is the position starting at which point?
L naught is the width of the reactant state.
L naught is the width of the reactants. So if you draw A and B, L naught is width of A going to B, or
not A going to B, A going to transition state. So if this is my transition state, and if this is my state A, this is L naught.
Right. That is L naught, and LD is the width of the transition. LB is the width of the transition.
This is LB.
Okay, got it.
Yeah. So ballistic motion basically says that once it reaches a transition state, it will easily go here.
Yeah. So now it includes LB takes care of the diffusion. Okay.
Right. So this is called diffusion limit or Cramer's limit. So there is a way to actually account have a final super master equation which will take into account both these extreme limits. So this is the lowest possible. This is the highest possible. So there is a way in which we can so now you see, but if you compare it, there is completely different terms in both these frequency factors.
Wait, I have a question.
Yeah.
Shouldn't we only worry about the lowest limit, the rate limiting step of whatever reaction that we care about? Why do we care about
Rate
the
limiting step is rate limiting step has nothing to do with the rate constant, right? This rate limiting step is basically determined by which has the highest energy barrier.
right?
We are trying to determine based on the energy barrier. We are trying to determine the rate constants. So this is an overestimation. This might be an underestimation. So we are looking at how fast or how slow a reaction is.
But why is diffusion Kramer's equation essentially? Why is it lower approximation? Like, I understand why the kBt by 2 pi h could be like, high. It causes k to be higher, but I don't understand why d by L not L. I feel that's more realistic. So it should give us like realistic values than estimating it to be lower rate constant, isn't it?
Because in faster reactions, you might actually not see diffusion.
Oh,
So
got it.
again, by diffusion is a physical phenomena that we see, but when we say diffusion limit here, we are not exactly saying that the particle is going to diffuse.
Right.
We're not looking at diffusion from a continuum point of view. We're looking at diffusion from a atomic. So basically, what we mean by diffusion here is the particle is going to random walk between the transition state and. But when your barriers are low, it's highly possible that the particle actually might not, do all these, back random walks. It might actually be more favorable for it to cross the barrier itself. And when it directly does that, especially when looking at very fast reactions, your
There's no
tendency of the
diffusion
system
involved at all.
and to slowly go towards it.
Yeah.
Right. So that is exactly what is taken care of by ballistic motion. So
Okay.
there are cases when you need ballistic motion. There are cases when you need diffusion. When you need to assume that okay, it's not exactly a smooth walk for the particle. It has to endure certain certain resistances. Like when we write that when we write that your rate constant is so when I write that the rate constant is some d divided by d minus d into dn by dx. This dx is actually your resistance, right? So as you said, this length, this lb, will be your resistance when your motion of the particle is slow. Whereas when your motion of your particle is fast, the length doesn't matter.
Got it.
What
Yeah.
matters is how high the barrier is.
Right. And also when LB is very, very small, that doesn't matter that much, right?
When your LB is very, very small,
It becomes ballistic.
Actually, I'll try to cover this like the next time when I get a chance to. I don't know when. But when we do that, you will actually realize that when your LB is very small, you will actually reach the diffusion limits. That is why we actually have to reach a point where we have a master equation. Like I'll write it down. But we'll try to derive this later on. Like there'll be some terms which so.
What is V here?
This is gamma. This is the friction coefficient. So this comes from your Mulchowski equation, Stokes-Einstein and all that. So yeah, this is basically this is your molecular friction factor.
Okay.
So for that, I have to explain Stokes-Einstein theory. I have to explain the Mulchowski equation, and I have to write diffusion. So there's no diffusion coefficient. So I have to write diffusion in terms of Stokes-Einstein theory in order to get this equation. That is why this is a separate 30 minutes, 40 minutes discussion altogether. So the reason why I'm just writing it down is I'm just showing you that this is your master equation.
Right.
right? This is your master equation for the transition state theory. Now, as you said, if your LB is very small,
Hmm.
if it is to zero, this term becomes zero.
Mm-hmm.
And what are you
It
left with?
mostly
You're left
becomes
with dBd by
ballistic.
ballistic.
Yeah. Got
So your diffusion transition state theory, when your lengths of the reactant and transition states are low, if the widths are small, it will automatically tend towards going to a ballistic transition state.
All right. Got
The
it.
motion tends to be ballistic if your width of the transition state is small.
Mm-hmm.
And naturally, when your reactant state is also small, then also it
Mm-hmm.
tends to be ballistic because if your length of the reactant state is small, it means that you have a larger number of particles, which means that you can have more number of atoms,
Yeah.
right? So
Yeah.
that is what ballistic theory talks about.
Okay.
Ballistic.
Mm-hmm.
So with that, with diffusion and transition state theory, we essentially accounted for whether what happens when ballistic motion is not there. No recrossing is something that transition state. There is something called the Banner channel approach, but I have not actually gone through the derivations and all that. I need to do that if I'm going to like talk about it. And if it is a quantum tunneling, it is a completely different story altogether. I mean,
Yeah.
may
I have one question. So when you do simulations to figure out the rate constant using Kramer's rate theory, for example,
yeah.
how many transitions need to occur? Like, what is there like a value to it to get the right K? Because if there is a
So
ligand binding
when you're
to,
doing simulations and you want to look at the so then you need to look at the free energy surface, right? So again,
you need to get
I
the
think
barrier.
when we do enhanced sampling, so the thing is that whether you're applying Kramer state theory or like ballistic transition state theory, what matters is how accurate is your potential energy or free energy surface.
Right. So
And the
you need,
same Kramer state theory, if I extend it to a multidimensional system, that minus V naught will become minus delta G or minus delta.
right, right.
That's one problem. I mean,
So to get
you-
Right. So to get the accurate delta G naught, you need to do that multiple times. Is that what you're
Oh yeah,
saying?
that is so your multiple transitions and enhanced sampling is a completely different story. It's not.
Hmm.
It has got is a more sort of thing. The reason you need to have multiple transitions
Hmm.
in enhanced sampling is basically when so that is the reason why some people prefer to call the free energy surface from enhanced sampling as a PMF or a potential of mean force.
Hmm.
So I'll take the example of metadynamics. It's easier to explain that.
Hmm.
So when you do metadynamics, and when you have a say a free energy surface like this,
Hmm.
it basically fills out all these wells,
Right.
right? Technically, it fills it out like this. So what it is essentially trying, so when you reweight the same surface, you actually write that your free energy surface at a particular position is equal to minus the total bias that has been added in that position. That is how we estimate the free energy surface.
Mm-hmm.
So what it is saying, so what do we mean by multiple transitions is that when the bias potential added at each point
Mm-hmm.
is such that your free energy landscape has essentially become zero,
Mm-hmm.
then you should be able to see multiple transitions happening. It'll be much easier for the system to like just go like this
Oh, and
because
then
you are
you can subtract whatever you have applied to get the actual
so
free
when you're
energy.
able to see multiple transitions happening rapidly, it means that you have essentially reached this point,
Right. Zeroth point.
particular surface. And when once you have reached the surface, it means that now you can reweight it accurately.
Mm-hmm.
So it's more of a so more when multiple transitions is more of a case of accurately reweighting the surface.
Yeah. Yeah.
Because the way your bias potential is added is basically you're manipulating the probabilities, right?
Mm-hmm.
Right, using this minus Vs term. So if your
Yeah.
actual probability is say uh, e raised to minus V naught by kBt, you're multiplying another term with this, right?
Yeah. So now you need to get the K from here, the rate constant for this transition.
Yeah, that is so that comes after you get this thermodynamic surface.
Free energy surface, yeah.
Yeah. Then you use Kramer's rate theory in order to get the this thing, your
Right.
kinetics. So
Mm.
again, Kramer's state theory, transition state theory itself is an approximation of the kinetics.
Yeah,
We are
yeah, yeah.
approximating we are calculating the apparent kinetics of the system
Mm-hmm.
through the thermodynamics because through enhanced sampling we cannot get the accurate kinetics of the system.
Right.
These are all apparent kinetics. All transition state theory, everything is like apparent kinetics.
Mm-hmm.
Like
It's
the
not
very
true
fact that the
kinetics.
very the no no the just imagine, I mean, the very fact that when we write transition state theory, we assume this is the free energy this is the potential energy surface. This itself is an assumption that we are making. This is an additional assumption that we have a hill shaped transition state.
Yeah.
What if we have a transition state that is like this?
It generally is like that.
Yeah, it is always like this, you won't see a perfect transition state like this. You
Yeah,
will never see
exactly.
this,
Yeah.
right?
Mm.
I mean, when you like derive a 3D transition state theory, you assume that this is like it's like a pyramidal type structure.
Right.
Have you ever seen a pyramidal type free energy surface? No, or a potential energy surface? Never. You never see. You always see something like something like this.
Yeah.
Some random thing.
Right.
So that is why transition state theory itself is it's an approximation of an approximation. You are using
Got it.
statistical. You are analytical. You are analyzing an approximate potential energy surface in order to just understand, okay, how can uh, how does the kinetics work exactly. You're just trying to decipher how kinetics work based on a thermodynamic barrier, right?
Yeah.
And
Yeah.
but the thing is that most of the cases, transition state theory can give you a very good answer. It may not be the most accurate, but it will definitely be in the vicinity.
Right. So if you were to compare two system, it's a good comparison.
Yeah, so this will never be the accurate kinetics, because kinetics of a system or kinetics of a reaction will never just depend on the energy barriers.
Yeah.
It depends on so many different things.
Yeah.
Compare the computational experimental like DFT and all. We make all these plots and all that for using energetic band calculations, and we say, okay, this is the energy barrier, so your kinetic constant will look like this. There'll always be some error between the experimental and the and computational rate constant, because there are other effects that happens.
Yeah.
We may not be able to address. So, so finally, the point is that that is why this is an apparent kinetics. So, but the reason why still people say it works. Just like ideal gas. There's absolutely no gas in this whole universe is an ideal gas. But still, we still use the ideal gas equation for even designing some reactors.
Yeah.
You
Yeah.
okay, no, the pressure and temperature are such that okay, we can use PV equal to NRT.
Yeah.
We actually used to learn in thermodynamics class that when your molar volume of your gas is greater than 30 liters per mole, ideal gas equation becomes a very good approximation.
Makes sense.
That is why when you deal with them, hypothetical gases and all that, space, gases in space and all that, hydrogen, helium and all that, you generally tend to use ideal gas equation.
Right.
Because there's absolutely no pressure in space, zero pressure.
Yeah.
So when you have low pressures and very high temperatures, either one of these two or both together, you can generally use ideal gas equation. It will be a very good approximation. It won't give you the exact answer, but it is easy. It will give you an answer which is close. So if you use ideal gas equation to get your molar volume versus using say something like a Redlich-Kwong or some complex equation and getting the answer, your difference in the answer won't be the same. It won't be
Mhm.
very different.
Mhm.
And typically, as engineers, we just want values in the vicinity. We don't really want to go into third digit, four decimal digits.
Exactly. Yeah, that doesn't matter. Most
Right.
of the industry
Yeah.
wise, you only worry
Yeah.
about money.
Especially in industry wise, if you can do something on a calculator, why do you need an Excel sheet? That is what people
Yeah.
ask in industry. Right? Yeah,
Yeah.
because every calculation that you do is a cost on the company.
Exactly.
And if you can do at a lower cost, that is what they want, because they're
Yeah.
in the business of making money.
Yeah. Yeah.
Right? So transition state theory is something similar. Transition state theory is the equation of kinetic.
Mhm.
Like we can that is the best analog that we can make. Like it is absolutely not real, completely ideal, but it works.
Mhm. Okay. All right then. Thank you.
Yeah.
Yeah, I think we
Thank
are
you
at
very
the end.
much for attending
Thank you.
today.
Thank you for giving a great presentation.